Okay, so this is one of my videos from chapter 27, and this time we're going to be looking at a couple problems with photons and the photoelectric effect and all that good stuff. So first of all, I wanted to point out, if I haven't said it in class already, I probably have, so I'm probably being redundant, but I just wanted to point out that this chapter we're doing a large reading guide over. Um, don't let it intimidate you because most of the actual problems will be asked are going to be pretty simple. We're just going to make sure we do the conceptual part of this last unit really in depth. The math is going to be minimal. If you notice on your formula sheet, there's like four little tiny formulas you're going to be using. So the problems shouldn't be that difficult. Some of the concepts are a little tricky. That's why we're doing them in depth. Okay, anyway. So we already have the fact that energy levels are discrete, right? In the quantum world, energy levels can only exist at certain integer values. The first smallest one possible being Planck's constant times the frequency of whatever type of particle you have or whatever photon you have. Okay, they've got in this little part right here, they've got a whole bunch about relativistic formulas. We're not doing relativity. We will do equals mc squared. I want to point out that for Einstein, when he in 1905 he developed 5 major papers, relativity is not the same thing as E equals mc squared. We will be working with E equals mc squared as the very last thing we do. That is not relativity. Relativity has to do with light's speed and time changing and stuff like that. So we're not going to look at that this year. We just don't have enough time. We definitely could, but we just don't have enough time. Anyway, so what's happened here is that on your formula card you can see that you have the quantized energy level for a photon can be expressed as h times its frequency, but it can also be expressed if you look down here and you just multiply this c up over there, then you can see it's also expressible as the speed of light times the momentum. P here means the momentum of the photon. Okay? So if you combine those, you can see that momentum, let's erase that now. The book is using combinations of these little tiny formulas, and that's going to be the key to most of your problems, combining these little tiny formulas in different ways. So you can see that you can solve for the momentum of a photon now by taking its energy, its total energy, right? It only has a total energy. We just talked about that up here and you answered it for your reading guide. Divided by the speed of light, and its total energy can be represented like this, based on what Planck did. So H, if you look at F over C, remember go back to the main equation. The main equation which you're going to be using a whole bunch is that the velocity of something is lambda, its wavelength times its frequency, right? And for this, the velocity is c, so that means c equals lambda f. We're going to use that over and over and over again. If you can do that, you can do most of this chapter, I would bet. Anyway, so then you can see that what they've said is they've seen f over c, so if you divide by c over here, you get 1 over lambda equals f over c. So that's how this lambda got there. So you can also express the momentum of a photon by taking Planck's constant and dividing by the wavelength of that particular type of photon. Okay? So that's pretty easy, just combining those little tiny formulas. I'm sure all of you can do it if you try. Okay? All right, so let's see one example here. This one says we've got a 100-watt light bulb. It's emitting photons, of course. It's a light bulb, right? And it says assume its efficiency is about 3%, so we're only going to work with that 3%. The other 97% just goes into the infrared as heat. So we're going to work with that 3%. And it says the average wavelength is in the middle. Okay, I believe you. 500 nanometers for this light. So then it starts to get into the equations, right? So the energy of each photon, each individual photon is going to be HF. We just talked about that a whole bunch. F is c over lambda. We just derived that in the previous video up here, right? F is c over lambda. You can see it right there. So you get that energy of a single photon can be represented like this. So it says only 3% of the 100 watts is emitted as light. So that's 3 watts. Watts are joules divided by seconds. So the number of photons equals that 3 joules, basically, right? So the number of photons equals that 3 joules. That's basically what we're doing here. So we're going to say n is the number of photons. It's this energy hc over lambda. So you can see that right. Oh, well, let's hold on for a second. So I skipped this part. Go look right here. So the energy emitted in 1 second is 3 joules. We talked about that, right? So that is going to be the number of photons that are doing that. So that energy is going to be HF times the number of photons. Remember when we did this up here, we did it for 1 photon, each photon. So there's going to be a certain number of photons, and I think that's what they asked us, right? See, we should be clear. I should follow my own problem-solving advice. It says estimate how many visible photons. So at the very beginning of the problem, I should have said how many photons. That's what we're trying to come up with. So first we did it for a single photon, and now we're looking at that same thing just multiplied by how many there are. Okay? So once again, we plugged this in right here. So we get n times h c lambda. And then we solve for n. So let's go do that over here. I don't know what they're doing. But so we get n equals the energy divided by HF, right? And we said F is C divided by lambda, so that's going to be E over H, and then down here we're going to have C divided by lambda. So then that lambda is going to get flipped up, right? Ah, there it is. So the lambda got flipped up to the top. We plug in and we get a number. Let's do significant figures. Basically, that's basically going to be like 1 times 10 to the 19th if we round, isn't it? So it's just 10 to the order of magnitude of how many photons we've got is 10 to the 19th photons. So that's how many photons are coming out of that light bulb every 1 second. Crazy, a lot of photons. But photons are really small. So that kind of gives you respect for Planck when he first figured out that energy was quantized. He was measuring really small amounts. That's why we're going to use electron volts a lot in this chapter. Anyway, so now this one says, suppose that those 10 to the 19th photons were focused onto a piece of black paper and absorbed. So we're thinking like a black body problem now, right? And it says calculate the momentum of 1 photon first. So momentum of 1 photon, hey, didn't we have an equation for that? Momentum was Planck's constant divided by wavelength. Do we have that? Planck's constant's a number, right? Done. Wavelength, what did we have back here? Was it this guy? 500 nanometers? Oh my gosh, I'm drawing over it. There it is, though. 500 nanometers. So we should be able to just plug that in. So we get that there each photon, right? We're doing 1 photon again, has that much momentum. Remember, it's nice to do your units here. Momentum is, if you go back to it, think of units wise, I think it's mass times velocity, so that's kilograms per meters per second, like that. See it? Okay. So what else did it ask? Estimate the force that these photons would exert on paper. This is the kind of questions they're going to ask us on the AP exam, I'm sure. So how much force do they exert? They're actually bombarding the piece of paper. So how much force do they push it with? So it's crazy that when you shine light on stuff, you are actually pushing it. It's just usually negligible. So let's use Newton's second law. So Newton's second law, you say, hey, I don't see Newton's second law down here. It's F equals ma. But don't we also have another version? Let me look on our blue card and see if it's on there. Another version of Newton's second law in the mechanics section. You have F equals ma. Is it on there? Oh, I don't know if it is. Well, I guess you could just derive it. It's not explicitly on the formula card. But if you remember, you could also write Newton's second law as change in momentum over change in time, if you think about this as mass times velocity and so forth. Okay? Anyway. So we could go derive that again. We're not going to right now. So, okay, so let's think about what's happening. So these photons get fired. They have an initial velocity, or momentum, I should say. We're going to use momentum of this. They have a final momentum when they get absorbed of 0, right? So this is a little weird here. Up here, I think they should have done this backwards. I think this is backwards. I don't like this. Like change in momentum should be like final momentum minus initial momentum. So I think they kind of have that backwards. And the time they said was in 1 second, so that's going to stay the same, whatever. So delta t doesn't change. I think they did this backwards, though. The final momentum should be when they hit it and there's 0. So it's going to be 0 minus that initial momentum times how many we had, right? So minus, we had 10 to the 19th of them. And then the momentum we had was like 1.3. Whoa. Or 1. So I think we'll get a negative answer, but whatever, it'll be the same amount of force. So a really small force, but nonetheless, when you shine light on stuff, it does produce a force. If you don't do it on just a black body like we've talked about up here, then it's going to be a harder problem because you're going to have to deal with reflectivity and stuff like that as well. But there we go. All right, now at this point, we're going to go do something with the Compton effect and X-rays. So if you haven't already watched the little like 2-minute clip from Mrs. Tao, I think that's her name, Mrs. Tao's video on the Compton effect, please do so. I think the book gets into it way too in depth, and she has a nice, really simple 2-minute explanation. So go watch that, pause this video, and come back to it. Okay, so now that you've watched the video on the Compton effect, we're actually going to do a problem with that. So it says this time Compton was working with X-rays, so these X-rays have this wavelength, and they are hitting a piece of carbon. She talked about graphite in the video, right? Like a pencil's made of. Carbon's very similar to graphite. Anyway, so we're going to think about them being scattered at 0 degrees, 90 degrees, and 180 degrees. So first, what is the main formula for the Compton effect? Of course, you don't need to know this. It's not on your little formula card, but the Compton effect says that the wavelength of these X-rays actually can change depending on how you do this. So the new wavelength is the old wavelength plus, and he used relativity, which we're not going to do to come up with this, Planck's constant, the mass, speed of light on the bottom, and then here's the angle part, 1 minus the cosine, and phi, that angle is the phi is the scattering angle, whatever angle you shot them at, how they impacted and stuff, okay? So first they said think of phi as 0. So if you make it 0, the cosine of 0 is 1, right? Go to your chart here. Here's cosine 1, 0. Cosine is x. So from the unit circle, we know that that's going to be 1. So 1 minus 1 is going to be 0. So this whole thing will be 0. So in other words, they wouldn't be affected. You're not going to have any wavelength shift in these X-rays, so they're not going to be affected. How about if you do 90 degrees? So and this is Tao's diagram. So you have like the X-rays coming in, right? The photon of X-rays. It's coming in. It hits this piece, a slice of carbon, I guess, but let's just imagine it as a particle of carbon. And now it says that they're 90 degrees, so here goes the X-ray afterwards. So I think that this time it's definitely going to have an effect. So if we put 90 into cosine up here, the unit circle would tell us the cosine is 0, so you get 1 minus 0 is 1, so you get the new wavelength is the old wavelength plus this amount. So you can see that it's adding basically about this many nanometers to the wavelength of that X-ray. So that X-ray is essentially a longer X-ray now. Okay, so now what about if instead of the X-ray bouncing off at this angle, what if that angle is 180 degrees? So in other words, the X-ray kind of goes in and then bounces off and comes back this way. Okay, so if that's true, then you're going to have this spot over here, so it's going to be -1. So you're going to have 1 minus a -1 is going to be 2, right? So that's why you get this 2 down here. So now the new wavelength of this X-ray is going to be the old one plus even more. So this guy is going to be like, I think, the most you could possibly get out in terms of change in this interaction. So it's going to be quite a bit longer, I would say. Well, I don't know. It depends on your definition of quite a bit. But, so that's how much that X-ray has been changed by in this scattering problem. Okay? Remember, I think that the most important comment Ms. Chu made is why does lambda even happen? We don't know exactly why this equation up here works the way it does, but I think the main concept to understand is that when a photon hits something, its speed, when we did like pool balls, when you do conservation of momentum and collisions, the speeds can be affected, right? But this is a photon. Photons have to travel at the speed of light. So if we go back to our equation that says c, or velocity, equals um, frequency of the light times its wavelength, the c part can't change. Its speed can't change afterwards in this interaction. So only the frequency and the wavelength can change. So the Compton effect describes how, particularly, the wavelength changes. Okay, see you next time.